Cutland from University of York, and he's going to talk about global attractors for 3D stochastic Navier-Stokes equations.
Thank you very much. Well, thank you for the opportunity to talk about this work. It's something that was done a few years ago, actually. It's not so very recent, but I think it's probably not too familiar to the majority of people, so I don't make any apologies for talking about it. And of course, it's joint work with Jerry Kiesler in Wisconsin. So the setting is the very classical setting of the three-dimensional stochastic Navier-Stokes equations in 3 dimensions, the difficult problem where we have all sorts of problems to do with existence, uniqueness, and so on. And the setup is the conventional one. We're working in a bounded domain in 3 dimensions, and we have a filtered probability space, and our initial condition can be random. And we have today I'm working with a one-dimensional Wiener process. The papers are written with that, but actually the whole idea can be extended to more general, even infinite dimensional noise. And the equations are fairly general because they're time homogeneous, so time doesn't occur in the forcing terms. But apart from that, the only restriction on the forcing term and the term driving the noise is the conventional one of continuous functions with linear growth, with a little bit of restriction on the linear growth, actually. So it's a fairly general setup. And when we're thinking about attractors, conventionally, attractors you get in systems where you have some sort of uniqueness. So you have a dynamical system or a flow or a semigroup, but without uniqueness you have problems, even defining what you mean by an attractor. With uniqueness, which you have in 2 dimensions, you can have different kinds of attractors, measure attractors, attractors where you're pulling the whole process, not going forward into infinite time, but you're going backwards to negative infinite time and seeing what happens at time 0. That's Flanderly and Kral developed that idea. But in 3 dimensions we can't do that. In the deterministic 3-dimensional equations, the problem of attractors was addressed by Sell, who took a rather sort of radical approach. When I first saw it, I thought, this is cheating, really. He said, let's replace the phase space where the solutions live, normally called H, by the space of complete trajectories in the space H. And so the points you're looking at now are entire solutions of the equations. And what Sell did was to say, well, there's an obvious semigroup on that space of paths, space of solutions. Namely, if you take a solution, the time, the operation st on that simply moves down to some time here, chops it off and moves it back, moves the time t back to time 0. So time translation gives you a semigroup, and what Sell did was to show that in that setting, in 3 dimensions, you have an attractor. That is a set of paths which is compact, invariant, and has all the attraction properties that you'd expect. So the thing is, how can we extend this idea to the stochastic equations? Well, there was some work done earlier with Franco and Schmalfuss, where they looked at a case where there was a multiplicative noise, which is what we're dealing with, but it was a rather special form, and it actually allowed you to do essentially pathwise solutions, I think it's fair to say, and so you could do the pulling back idea. And then with an additive type of noise in a slightly more general setting, you can do the same sort of thing. A sort of pathways approach. But in terms of a truly stochastic setup, Nothing, as far as I'm aware, has been done. So our idea was simply to work at the level of processes rather than paths. So instead of the objects of concern just being individual solutions in the deterministic setting, the objects that we deal with are complete stochastic processes, the whole thing. Now, if you're going to have an arena, a playing field where all this makes sense, you've got to have some sort of probability space which is going to have built on the same space with the same driving Brownian motion a whole host of solutions. There's got to be a lot of space, room in the space for a lot of things to happen. So the solution to this problem, which I'm going to describe, is based on a lobe space, which, as some of you know, comes from non-standard analysis, which I won't be going into in any detail at all today. But basically, I'm going to spend time just sort of setting up the idea and the problem. So just briefly, a recap on the conventional setting of the Navier-Stokes equations. You have the various spaces H and V, and the operator A, and so on. And you have these finite dimensional spaces which play an important part in solving the Navier-Stokes equations. And then we have this the problem, the operator that causes the problems. And so once you have this functional analytic setting, you have essentially, I think of it as a SDE in the space. Well, it's in the dual of V, but actually it turns out the solutions live almost all the time. They live in H. Just a note there to say that this whole idea does work for more general noise processes other than a one-dimensional process, but just for simplicity we did it with this in this setting. Now, so as far as the assumptions on the coefficients are concerned, very conventional sort of assumptions that you would need to get solutions anyway, with a small restriction on the size, on the rate of the linear growth, determined by the viscosity here, and this is the first eigenvalue of the operator A. The reason for that is in order to sort of pull the energy back down so that you get some sort of decay. So I suppose by now, classical theory of stochastic Navier-Stokes equations gives a weak solution to the equation, this equation here, even without the final condition H4, but we need H4 for our purposes today. So very conventional, very classical. Now, if we're going to mimic Sal's idea of taking a path and shifting it, chopping it off and then shifting it back to zero, we can't actually do the same thing because of the adaptiveness requirement. So we've got to actually assume some extra structure on the underlying space. Well, the way to do that is to assume that you've actually got the space equipped with some measure-preserving maps, which actually have the semigroup property, and this is the important one. The map theta t changes the sigma algebra fs in the filtration to ft plus s. So it's essentially and it has this effect on the driving Brownian motion. And if you think about what theta 3 says, it's that the increments of the sort of shifted process are the same as the unshifted process. So if you just think of the noise as being shifted by t to the right, this whole thing makes sense. So if I think of it like this. Whatever's going on in terms of any solution, you've got noise going along here, and if this is the noise, then we're shifting the whole noise by a factor of t. That's what these measure-preserving transformations do. So that enables us to make sense of various things. And in particular, you can take, if you've got a stochastic process, doesn't have to, any stochastic process that's adapted, then you can do the shift or the semi-flow by, in terms of the time, if we're doing the operator SR here, we do a time translation by R, but then we have to modify the noise using the theta. And that essentially takes a process that's, if we imagine a process with all its powers like that, then what we do is you take the process, which goes on like this, we chop it off there and then take this bit and move it back to the origin. And so by that means, if it's a process defined for all time, then we get a new process defined for all time that's also adapted. So it's a sort of shift along of processes. So a few obvious remarks. It's a semigroup on the class of stochastic processes, and the shifting retains the adapted property. And then you get the obvious relationships between both stochastic integrals and deterministic integrals. If you can see what's happening, if you integrate the shifted process, then it's the same as, is that right? Yes, if you integrate the shifted process from 0 to t, it's the same as integrating the non-shifted process from r to r plus t, provided you do the obvious changes on the probability space. So it all works out as you'd expect. And this is actually translating these facts up here into the situation of let me see, yeah. This is if you've got a solution. This is saying if you've got a solution to an equation of some kind, that's what this would be here, then the shifted process is also a solution. So everything makes sense. Now, just to set the whole thing up, we're going to have some metrics on various spaces. So we want the space of powers, individual powers of a solution. They are powers in the Hilbert space, and we want a norm on powers. That's a fairly natural one. It's not too important exactly what one you take. It's just that you want the norm of paths to be almost surely finite and the expectation to be finite. Or actually, you want it to be in L2. So we have the norm of a entire process now, given by taking the norm of the path and taking its L2 norm. Again, fairly natural sort of way to do things. We're going to want to talk about laws of processes, so that's just again a bit of notation. And we also will need the idea of, if you've got a process, say a solution to the stochastic Navier-Stokes equations, we want the pair of processes of the solution and the driving Wiener process and the law induced on the product pair. And then a bit more notation, because we want actually some metrics on these spaces of measures, spaces of probabilities. These are the appropriate metrics. The space of probability measures on the path space, the distance being the Prokhorov distance plus this other term here, and the same with measures on the product space. This is all just some of the technicalities. Don't worry too much about that. Now we get to the point where we can actually define what we mean by an attractor in this sort of setting. Well, let's suppose we've got a class of solutions to the stochastic Navier-Stokes equations. A class, which I'm going to define later, there's a natural class which comes out. But let's suppose we've got a class defined, and it's a class of solutions big enough so that whenever you shift a solution in that class, then it's also in that class. then the definition of an attractor is a little bit convoluted, and I'll explain later a better definition. But the first definition that we came up with was this, that we start by looking at what we call a law attractor. So that would be a set of laws of solutions, but not just the laws of the solutions, the law of the process which is the solution, together with the driving Wiener process. So we call that a law attractor if there's invariance under the semigroup which is naturally induced by the one that we're given in the first place, the shifting semigroup. The normal properties of an attractor. Attraction then for bounded subsets of laws are eventually contained in an open set which is a superset of the attractor, and we have compactness in the metric. That was the reason for introducing the metric on the space of measures on the product. Now, what we'd like then is to say, well, what's an attractor in the sense of a set of processes that's an attractor? And first of all, we say that it's a law attractor. So if we look at the laws, we get an attractor in the sense above here. But then now we're looking at processes. So we want the set of processes to be invariant in this way here. And then attraction, which is not quite the normal sort of attraction. I'll say a word about that in a moment. And then you'd hope for compactness to be your final condition. But we can't get compactness. In fact, we can prove, or there's very, very strong evidence that it's not going to be ever possible to get compactness of an attractor in this sort of setting. That basically the space is going to be so large and the attractor is going to be so large that it's not going to be compact, but it's actually going to be very close to compact. So it's a bit of a hybrid definition and not entirely satisfactory, but that's what I want to work with to start with.
Is the reason that it's so large that there is just tons of stuff in the probability?
There's tons of stuff. Yeah. There's just so much stuff there. I mean, even to get a space that carries a solution anyway, we know we have to enlarge. The Wiener space doesn't carry solutions, so you're always going to have to enlarge to get solutions anyway. But there's just tons of stuff in there. So this is what I've just been saying, that it's too much to expect compactness. Now, the attraction property, which looked a bit technical, is actually equivalent to the normal sort of attraction property of bounded sets being attracted eventually into an open superset of the attractor, but only for open sets of a rather special form. Bit of a nuisance, that. But now here's the sort of remedy to this unsatisfactory aspect of the definition, that there is actually a stronger definition which one can make, which we call a neo-attractor. Unfortunately, the very definition of a neo-attractor is something that requires quite a bit of non-standard analysis because it comes out of that. So I'm not going to even attempt to explain what that means today, but I'd be happy to try to later, but afterwards. But the point about a neo-attractor is that it attracts. We get a neo-attractor as an attractor in the sort of normal sense, except you put neo in front of everything, really. So it's it's neo-compact. This is with the definition. It's a neo-compact set, but that is a concept slightly weaker than compact. And it attracts bounded sets into neo-open sets that contain the set A. And that's a slightly stronger definition than ordinary open. And the point is that neo-compact sets are quite close to compact sets. They are closed, they're compact laws. And actually, so we can formulate the definition without having to talk about this laws. And so we get a definition which is not in any way a sort of hybrid definition. It seems the right sort of definition. Okay, and it is a stronger notion than the one I've given you. Anyway, for today, because I can't define a neo-attractor, I'll have to stick with the previous definition. Now, if we just go back to the definition itself then, which it's not hard to show that if there is an attractor, there's only one. And if it exists, then the set of laws is compact in the metric on the path space. And there's an attraction of a bounded set of laws. Let's see. Yeah, there's also attraction at the level of processes in this sense here. So the set of processes with a given whose laws are in a given open set are that eventually attracts bounded sets of processes. So just a technical fact that comes out of the proof I'm going to give you, or I'm going to outline later, that the attractor is simply a countable intersection of the application of the semigroup to any bounded set, and if we apply that in particular to this set of law inverse of the laws of A, we get that A actually can be defined in this way. But the point about that is simply that although A is not compact, it has a definition in terms of a compact set of laws. So it's it's quite close to being compact. Okay. So all this is relative to a yeah.
Just to relate that to the sort of more usual setup when you have uniqueness of solutions. So
Yeah.
if you had uniqueness of solutions and you think it's your nice random dynamical system,
Yeah.
then your definition of an attractor would be, in some sense, would correspond rather to the definition of a random invariant measure, rather than that of a random attractor.
I would think so. Yeah. Yeah. Something like that. Yeah. 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 If you had, then I'll think about that. Yeah, but that's right. I mean, once you have uniqueness, you can think in terms of random attractors. So you can think of things at the path level, really. So that this attractor here is not a random object. It's a set of processes. It's not random at all. So in a sense, we're into classical dynamical systems without any randomness. But it's just that the objects concerned are these stochastic processes. So the main theorem then, the summary is that there is a space which I'm going to describe, and there's a class of solutions, and that class of solutions it's a big class. It has solutions for any conceivable initial condition. There's a solution with that initial condition in X, so it's a big class, and there's an attractor for this semiflow, and it is actually a neo-attractor. Okay, so now I need to just describe the class of solutions that I'm talking about. Yeah.
In the spirit of Martin's question, if you look instead of two-dimensional equation, what you get? What would be the result in your framework? Would the result be stronger? Some statement of.
You certainly get the same result. I mean, I think you probably get it even for 4 dimensions, in as much as you can, so you can go the other way. But for 2 dimensions, yeah, you just wouldn't even think of doing this really, because you wouldn't need to go to processes, because you've got.
I understand. But
yeah.
My question is that you said that your attractor is not compact. Would it be compact in a 2-dimensional case, or?
I'm not sure. I'd have to think about it. Probably not, actually. I'm not sure. I'll have to think about that.
Okay.
Yeah. So let's see what this space of this class of solutions is. Well, it's actually more or less what you'd expect in terms of defining any solution. You usually restrict to the class of solutions which has these path properties, so there's nothing unusual there. And that second condition is simply saying that it's a solution. Now here's something a little bit specialized now to this our particular case, because the class of solutions that we're defining is relative to some constants which are going to come out later. So, but in advance, if we're given any constants, we can define this class. And in this case, what we're saying here is that there's a sort of energy decay here, which is what you'd expect to need if you're going to get some sort of attractor. And a similar sort of thing at the level of the energy plus the integral of the stronger norm here. So this is all fairly classical. The quantities one's looking at here are fairly classical, but we want some control on the way this grows.
The result is so general that it could be applied not only to Navier-Stokes.
Probably, yeah. Probably.
Was something special about Navier-Stokes, which you could axiomatize more or less?
Well, I suppose the thing about Navier-Stokes is that there's a classic example of something which has non-uniqueness because of the problematic term, and yet along with the non-uniqueness, you have some control over what's going on through the energy and so on. So the generalization would be to systems like that. Because if you have systems that don't have uniqueness, then you've got to have something else in the system to control them, I suppose, really, which in the Navier-Stokes situation is the energy.
But it works also for ordinary stochastic differential equations. One could do this setting for.
Well, it depends what sort of equation.
We don't have uniqueness, for some.
Yeah.
Ordinary stochastic differential equation.
Yeah, you probably could actually. Well, yeah. I mean, the thing about Navier-Stokes is you have this quadratic term, which makes even solving them more difficult than an ordinary stochastic differential equations. But yeah, I guess probably any system where you can solve them and you have some sort of a handle, one could set this thing up. So where have we got to? We're just sort of defining the class of solutions, and then finally, well, this isn't the last condition, but we want the integral of the energy, at least up to time 1, to be finite. That implies that it's actually finite for all time, the integral over the whole of time, because of the decay here. And then there's one technical condition which is looks a bit mysterious. It's actually a uniform integrability condition, really, when you look into it. But there are these sort of truncation functions, which are they're designed when n is large. They're actually designed to throw away what happens for small values of u and just to concentrate on what happens for large values of u. Because for integrability conditions or uniform integrability conditions, it's what happens when over the large values when you're integrating that causes the problems. So this is a means of sort of focusing on that. Now, so the class that I've defined does depend on what these constants are. But here's the main point: that if you take the Navier-Stokes equations and just do heuristics on them, pretend you can use Ito and so on, although you can't. You can actually obtain constants which give these conditions. And when you construct solutions to the stochastic Navier-Stokes equations in any sort of natural way, whatever your favourite method is, I know what mine is, but probably different from yours. But the certain values of these constants just drop out naturally. So in that sense, it's a natural class of solutions, I would claim. Another way of looking, by the way, at this equation here, this actually can be derived from the Fourier equation, for those who know about the Fourier equation. Of course, the Fourier equation itself is something which one derives heuristically. The final point is that in the previous slide I defined these sets, the subsets xk are sets where the integral of the energy from 0 to 1 is bounded by k. There's a bracket missing there, and boundedness in the class of this particular class of solutions, boundedness is the same as belonging to one of the xk. So they're sort of yardsticks for the boundedness of sets. Now, next thing is to define a space and a set of solutions with the appropriate k's, constants on. Now, this is where a bit of non-standard analysis comes in. We start by taking the set of what I call the non-standard space of non-standardly continuous functions. Now, I think a lot of you probably think this is a mysterious, living in some sort of universe sort of on a few planets away from here, but actually it's not, because I've written it down here. Just there's on the blackboard here, if you can see it, the non-standard reals, or the hyperreals, are algebraically nothing other than a countable product of the reals modulo some equivalence relation. So there's nothing, that's algebraic, it's not mysterious. And in exactly the same way, the class of non-standard continuous functions on the reals is a countable product of the continuous functions modulo an equivalence relation. So it's all very algebraic, very rooted in ordinary mathematics, and not on some sort of planet at the far end of the solar system.
But in this definition, you take standard functions in C0R.
That's here, yes. Standard functions.
Not non-standard, it's the power of non-standard.
They're the non-standard. The star gives you the non-standard one.
Yes, but on the right-hand side, you don't have any.
No,
so C0R is standard.
Yes.
But
yes.
you said that it is of non-standard continuous functions.
Well, it is. This what we constructed here, the star of this object is what we call the non-standard continuous functions, and it's simply essentially an ultra product of the standard ones. And that applies to any mathematical object. You can do that. I mean, the machinery of non-standard analysis enables you to do this sort of construction all at once for everything, because you have a large arena where all your mathematics is taking place. So, you know, some sort of set within which everything you're interested in lives, just a mathematical set, and you just take an ultra product of it. So it still lives inside the ordinary mathematical universe.
Could you repeat maybe the definition of ultra product?
Yeah. Okay. Okay. Where shall I go? So an ultra filter. Do I need an ultra filter? It's a maximal filter. Okay, so on the natural numbers it would be, and it's the same thing as, if you like, a 0, 1 valued finitely additive measure. So if we think of it in this sense, let's call it M. M is a mapping from a function from all subsets of the natural numbers. Everything gets a value. It's finitely additive, and it needs to be non-principal actually, which means that the measure of a finite set is always 0. So the finite additivity means that the best way to think about it is to think of sets of measure, subsets of measure 0 are small sets, subsets of measure 1 are big sets, and you have that the intersection of two big ones is big, and the union of two small ones is small, and so on. So that's what an ultra filter is, and then the equivalence relation on say Rn, or any mathematical object, but take the reals as an example. If you have two elements in here, they're equivalent with respect to either the ultra filter or the measure. Let's call it the ultra filter. If and only if the set where they're equal is in the ultra filter, or another way of putting that is to say that AI equals BI almost surely with respect to this measure. So two sequences in here of real numbers. They don't have to be convergent sequences. Any sequences, all sequences are in there, but you say that two sequences are the same if they agree on a large set of indices. It's a very simple algebraic construction.
You have to believe in the axiom of price.
You do,
that
yeah.
These things exist.
Yeah.
So your construction is based on the choice of your ultra filter?
Yes. I mean yes.
There are many.
There are many. Yeah. So the result is an existence result. It's not a uniqueness result. Even in terms of the space. So anybody who doesn't believe in the axiom of choice is free to leave the room now. Okay. So, and then you do the same thing at the level of functions. Two functions, or a sequence of functions, is two sequences are the same if they reckon to be the same if they agree on almost all indices. And all the operations that you do on things are defined point-wise. It's not hard, shall we say? I was going to say it's easy, but the power of the whole thing, of course, is not in the definitions are easy. The power is in some of the theorems that tell you how these very rich objects behave. Anyway, let's go back to the space. Then we've got a collection of objects which are the sample points of our space. Each object in omega is a non-standard function from the hyperreals to the hyperreals, or a function from the hyperreals to the hyperreals. Okay. And you can define a canonical process in the obvious way, where now the time set is the set of reals. So it's a two-sided Wiener process, except that it's a sort of non-standard version of that. But a bona fide mathematical object, and you when I say internal, by the way, internal simply means is another word for non-standard. So in this sort of non-standard arena, you have a probability space, which is a probability space from that point of view, and you have the natural measure preserving maps at that level, which is simply the shift of the noise to the right. Now, from this sort of non-standard object here, with a But bearing in mind that this set here, the carrier set, is it's a bona fide mathematical object. It's a set. The lobe construction, which can be done very quickly actually, and if you believe in the Theodoric extension theorem, converts this object here into a probability space, a genuine, ordinary mathematical probability space, but having the same carrier set. You see, the set that everything's living on hasn't changed, so it's very rich, but the measure is being changed to make it have standard values between 0 and 1, ordinary real values between 0 and 1, and it's also sigma additive. So there's a half a page construction to do that. So that's the space, and you construct a filtration on it using the non-standard sigma algebras. Can be used in this way to produce a standard right continuous filtration. All this is fairly classical. I mean, it's been known for about 20 or 30 years now. And then I haven't got time really to talk about the standard part operation, but I'll draw a picture for those of you who've seen this before will be familiar. But if you have if this is the non-standard reals, and so you have a continuous, a function which is non-standardly sort of continuous. So on an infinitesimal level, it can have lots of variation, lots of movement even inside an ordinary real point. But for almost all of the paths in this non-standard process, you can actually smooth it out and get a standard continuous function. So that's sort of Anderson's contribution to this whole thing very early on. So by taking what we call standard parts, we convert a non-standard continuous path into a standard one, and that gives a Wiener process. And the transformations that we're going to need are simply the restrictions to ordinary time with the ones that we got before. So there's nothing difficult there. And we have now we've got a probability space, a very rich one, with measure preserving transformations, and that means that our semi-flow of processes is defined. Okay. So having got our space set up, then the question is how about this defining or constructing a class of solutions satisfying the conditions I gave. And so the theorem is that if you choose your constants carefully, on the space that we've got, there's a class X which contains a solution for any given L2 condition. Well, the construction is actually...
sorry, what is it? I lost the connection between X and L2 omega H. Somehow your process leaves L2, or is it?
Yeah, we've got, okay, we know what omega is. It's a probability space. We know H is.
Standard.
Yeah. So we know what L2 of H is. So our initial condition for a solution for Navier-Stokes equations, initial condition, a measurable initial condition which is measurable with respect to F0.
Okay, this is the initial condition. Sorry, okay, I got it.
What's the initial? Well, if you for any initial condition which is random, we can get a solution which has that initial condition.
Just because you say UT or omega belong to X.
Oh, I don't mean you. I mean you Ben. U zero, not U0 of omega. Sorry, I understand. Sorry, that's a mistake of mine. Yeah, it's okay. Sorry. So just briefly, how do you solve how do you construct X? Well, we know what X is. X is now is defined, but we want to show that X is non-empty. That's essentially what we're doing here. And the way to do that is to take a Galerkin approximation at the non-standard level, but the dimension of that is n for some infinite n, which makes perfect sense in the sort of non-standard analysis setting. So essentially we've got a finite dimensional SDE really here. It's finite dimensional from a non-standard point of view, and so your favourite book on SDEs, you'll find the theorem that tells you that equation can be solved. Because one of the key theorems of non-standard analysis is that whatever is true in the ordinary sort of setting is also true when you put stars on things. So in a certain sense, all the properties of the hyperreals are exactly the same as the property of the reals, as long as you explain that carefully. So all properties of finite dimensional SDEs hold for hyperfinite dimensional SDEs by this transfer property. This is the beauty of the whole subject, is that you get an awful lot of powerful stuff for free. So you just invoke ordinary SDE theory and the usual energy considerations, and we get a non-standard or internal solution. So this is a solution whose underlying space is the omega. The time is running through positive hyperreals, and we just take any one of those, any one such solution. And I say it's routine or classical. In other words, this was first done 14 years ago, so I suppose that makes it classical to show that this non-standard object that you've got here, a solution to this equation, you can take a standard part. In other words, you can sort of push it down by throwing infinitesimal bits away, and you can get a standard solution. It's a solution, and if you analyze this equation and do a bit of finite dimensional stochastic analysis, but at the non-standard level, just the normal sort of tools, these constants just drop out. So in that sense, the constants are natural as constants that give a solution to this theorem here.
Why is it that you lose the uniqueness?
Where
in the standard finite dimension? The non-standard.
There's lots of infinite natural numbers.
Well, I think for uniqueness of this sort of SDE, you'd want something Lipschitz conditions or something, wouldn't you? Continuity of the coefficients is not enough for uniqueness, is it?
They are Lipschitz. Finite dimension.
Yeah, maybe it is. Well, maybe it's.
Maybe it's
I think don't you all normally have to have some Lipschitz conditions to get uniqueness? I don't know. Anyway. It's not important, but so if it's unique, it's even better. You don't have to pick one; you just take the unique one. So it doesn't. So we've got a space, measure preserving maps, and a flow of processes. We've got a class of solutions that it's non-empty. I mean, that's essentially what we've proved. We've got it's almost routine to show that the class of solutions X is closed under the semigroup, and we've got the concept of attractor. So where do we go from here? Well, it's not hard actually, given the decay of the energy in those conditions on X, to show that you can get an absorbing set. That is to say, a set that eventually captures all bounded sets. And the fact of the matter is that if you just do the usual construction of this intersection of all the what happens to the absorbing set, you get an attractor. But of course, the hard part is to show that first of all that's not empty, that there's anything in there, and then of course it has all the right properties. So it's easy to identify it, but it's hard to prove the properties. Now, so what's involved in doing that? Well, we have to go back up to the non-standard world actually, because we want some sort of handle on this class of solutions. Remember, we showed that this set that there are solutions in here for any given initial condition by taking standard parts of things that we constructed non-standardly or internally. But not all. Well, there's no reason to believe that all solutions in X are of this form. Actually, no reason at all to suppose that. So, but we do want to make use of the richness of the space and the set X that we've got. So what we have to do is to define internally or non-standardly a class of approximate solutions. So these will be U's that are not necessarily solutions of the non-standard SDE, but approximate solutions. And here's the idea. I won't go through all the details, but here's a couple of examples. Right. Well, right. Back to the definition of X itself, we obviously want one of the conditions is that U is a solution to the equations. Well, you replace that by saying that a much more complicated sort of way of saying it, but you can see that this is looking at coordinate by coordinate for the finite coordinates, and this has to happen for all n. So we're looking at a coordinate-wise. This is where the fact that it's a weak solution means that this is essentially going to be enough. We don't require equality of the equation. We require that the difference between the left and the right is essentially smaller than 2 to the minus n for any n. So we require that for all n, this sort of approximate condition holds. So it's a bit tricky to get this right, and this was part of the hard work to know exactly how to define these internal approximate solutions. Here's another example. The energy, this general sort of energy decay thing. Well, we want it to be within 1 over n of the right-hand side for all n's and so on. So I won't bore you with all the technicalities, but suffice to say that there are these approximate solutions, and we also need to know what are the non-standard, these even the approximate solutions. We need to know which of those can we bring down to something standard. It's actually an integrability condition, because what can happen with anything which is random in the non-standard world, it can have very large infinite values for very small sets, which means it actually can be impossible to bring it down to something standard. So having defined what we mean by those non-standard things that we can bring down in this way here, we prove that everything in our set X is the standard part of one of these approximate solutions. So the point here is that we've now got a handle on these standard solutions, and the set X. We've got a handle on that upstairs, where in the non-standard setting, where there are a lot of powerful techniques that we can use. We define the non-standard, or the internal semi-flow. It's defined in exactly the same way as we did before. You just move to the right, shift to the left, and chop the thing off. So, and at the internal level, we get that the approximate solutions are closed under this shift operation. And the same thing actually happens for those that we can bring down. And this is quite important, because it's saying that when you the taking standard parts, that is to say the bringing down to earth operation, commutes with the operation of the semigroups. Then you show that there's a set which is what we call S-absorbing, which simply means in this case that one of these sets of internal solutions, that means internal solutions whose norm is bounded by a certain number, finite number of rho, that we get this absorption into the set B. And then, again, still at the non-standard level, you make the natural definition of what you might expect to be an attractor. This is what we had before. Let me see if I can find it. No, I've lost it. Anyway, before, if you remember, what we did was to define the set A as the intersection of these objects where we have S and A and or standard times. Now, here's a sort of one of the remarkable facts that happens in non-standard setting, that the intersection over finite times of these shifts is exactly the same as the union of all you get by shifting for infinite times. So this captures precisely the idea that what's an attractor about? It's what happens out there at infinity. Well, non-standardly, you can actually go to infinity, and we actually do have mathematically this equivalence between the two ideas, what you approach through finite times and what you get to at infinite times. And once you have this here, you can see that this, again, non-standard object has just precisely the right sort of properties you want, because if you shift by a finite time, if you shift anything in here by a finite time, well, infinite plus or minus a finite time is infinite. So you get the invariance trivially. The attraction comes out almost trivially. And then the key thing that gets the compactness or the neo-compactness is that this set here of non-standard set consists entirely of solutions that you can bring down to earth. And so we actually get our absorbing set by bringing down to earth the solutions or the processes that are in the absorbing set, and the attractor is simply the standard part of this non-standard attractor. So that's the idea, and I'm not going to go into any more details, I don't think, than that. The invariance and the attracting properties come from the fact that the set C had those properties in the non-standard world, and the compactness property comes from this, because there's actually a very nice theorem, goes back to Robinson, about any non-standard set where everything is near to something standard. If you bring it down to something standard, it's automatically compact. It's a very, very powerful idea. And this is really a generalization of that idea. Well, that's about it. Few concluding remarks. As I said, the fact that the non-standard attractor is entirely contained in processes that you can bring down to earth, that's what shows immediately that the standard attractor is what we call neocompact. This is in the sense of Jerry Kiesler and his student and collaborator Sergio Fiardo. Now here's a piece of interesting information. Fiardo's actually left mathematics, and he's currently, I think, Tom, do you remember Sergio Fiardo? Probably don't. He was a student in Wisconsin when I was there. Anyway, if you learned nothing, that's something you'll have learned today. And then, not surprisingly, perhaps, if you know about attractors and so on, is that the attractor we've got is actually restricted to non-negative times of all two-sided solutions. So that's a standard characterization of this attractor. And then finally, the non-compactness I was telling you about earlier. Hard to define what we mean by reasonably rich, but any space, I mean, the feeling is that any space which is rich enough to do all this sort of activity is actually going to be a space which is so rich that the attractor can't be compact. So you're forced back to this slightly weaker definition of neocompact, which actually seems to capture exactly what we can get. And then a couple of references. These are the two papers that the talk's based on. Thank you very much.
Can you show again the main result?
Yeah. I suppose. Well, okay. That's one way. I mean, there's different ways to put the main result, but here's one way to put it. We can define a space and a very natural class of solutions that is. Sorry. Is that the one? I mean, is that
okay.
good enough? So
maybe trivial question. In a sense, in the classical situation, you use compactness in a sense to prove it is non-empty.
yeah.
So is it neo-compactness which somehow does the job, or?
It's the other way around, as it always is, and what always seems to be here, where you do your construction, and as a result of what you constructed, you see that what you constructed is non-empty and that it's compact. In fact, when we first started sort of showing how you can get solutions to Navier-Stokes, even before the stochastic Navier-Stokes, you find that where you have specialized compactness theorems, often you have to look at what you've got, because you want to get convergence of Galerkin approximations. All right, so if you want convergence, you've got to find the right topology. You've got to find a compactness result that enables you to pick out a convergent subsequence. What seems to happen in using our machinery is that you construct something standard. Something comes out, which is a genuine solution, and then you say, but that's a compactness result. So you get your compactness result as a byproduct rather than as a tool that you have to sort of manufacture in advance. So it's just sort of, it turns everything upside down.
Thank you.
Any other questions?
So in the case of uniqueness, suppose you have uniqueness. Then you take this space X and project on the initial functions. Would you get compactness? The attractor will
You mean
print
you mean the
classical
so the set of initial conditions for the initial conditions would be a collection of random variables.
Fixed points in H.
By definition, the initial conditions have to be random here, because even if you start off with a fixed initial condition rather than a random one, the moment you sort of move along, chop the thing off and move it back, you've got processes which have got random initial conditions. In the
case of uniqueness, you have a projection between H and the process space X, because there's only one.
Well, but that's if your initial condition is a fixed point.
Fixed point.
Yeah, but in this case, by definition of the problem, your initial conditions are always going to be random.
But if you have uniqueness, then
uniqueness for what though?
Uniqueness of solutions.
For
weak solution.
Yeah.
Then.
But in this case, that would be uniqueness for any initial random initial condition. You'd have uniqueness.
But not for fixed?
Well, also fixed as a special case.
So if you take for fixed, then you can identify that with all the processes through that point.
But we are looking at processes that are random at time 0. You have to. Yeah. We'll talk about it over competition.
Okay, so let's thank Nigel again.